Alright, welcome to ELEC 3067 26 summer, Fanshawe College, London, Ontario, and today is June the 10th, 2026. Well, must be the summer hours or the summer whatever it is, because I don't see too many people here, if anybody at all. Well, I'm going to conduct that. See, maybe some people are counting on this thing being online, which it always is. So maybe that's the strategy that just happened. Okay, so let's get on with this lesson here. Today we'll be talking about three-phase transformers. All right. Let's start the show here. Now, before we before we do this, I want to point to you that there will be a test. You see here, there's those quizzes. There are short quizzes. We had a pretty good review of the materials yesterday in person. And whoever was there benefited from the review. We did some problem solving and some of the reviews on what things are, how things are being called, and terminology and such. All right, all right, Love Breed, welcome. Okay. Now those quizzes 2, 3, 4, and 5. They are very short quizzes. I would strongly encourage you to do them. They're not worth much. They're 1% each. However, the weight that they carry is that they help you, and they will help you. I guarantee you that they will help you on the upcoming test, which is next time we're going to see each other, right? Which I announced in person, our class in person. It would help that if more people were present, but those who were, maybe they're going to spread the news, but that's all I can do. All right, so I'm going to follow up with the general announcements and email. However, that the test is listed in the course plan, course outline, and it was announced. And well, I just hope that enough people will show up to to actually do the test in class, in person. Right? So bring your pens, calculators, and what else? Yeah, helping sheet or formula sheet or crib sheet, as some people call it. You can write any kind of terminology, anything that would help you, that you would think that would help you with the test formulas. You can write on both sides of that paper. All right. So let's get on with this three-phase transformers. Okay. Again, let's start this. So three-phase transformers, as always, there's a review, three-phase transformers, voltages, and of course we're going to summarize what we just did. All right, three-phase systems. We have three waveforms separated. There are sine waves, or, well, sometimes we like to call them cosine waves. Either way, it doesn't matter where you start. It's going to be a sine wave shape. All right, and those sine waves or cosine waves are separated by 120 degrees on the timeline. All right? So phase, the voltages on phase A and phase B and phase C, here's the relationship between them. So the voltage on phase 1 is the square root 2 of the peak voltage, all right, times cosine of the angular velocity with reference to time, which would be the angle. If you do the angles in degrees, that angular velocity, you just have to make sure that you include this here, the angular velocity in degrees. All right? So that's going to this would be the positioning within 120 degrees with each other. You see here, that first one starts where it starts. The other one starts 120 degrees later, and the next one starts another 120 degrees later, and this is how they relate to each other. Phase 1, phase 2, phase 3, whichever color you want to use for that. Separate them by 120 degrees, so 1, 2, 3, there you go. Alright, now when it comes to connecting transformers, or, well, coils, in Y or delta configuration. Now, I'm going to get my board here. This here, when we have, let's say, 3 coils, we connect them like this. Here's a coil, and here's a coil, and here's a coil. They are all joined right in the middle, and they're connected to phases. Alright, and here is the neutral. So you could have phase A, phase B, and phase C connected to that, and we have a neutral. So this would be the Y configuration, or star configuration. And in this case, what we have is that the line voltage with the reference to the phase voltage, and then there is line current, and here is the phase current. Now, where is the line? This right here is the line. Alright, line, line, and line. If you want to measure line voltage, you would measure the voltage between any of those two lines. Between line 1 and line 2, or line A and line C, or between line A and line B, and between line C and line A. Any of those two lines, that is going to give you the line voltage, E line. Alright, now here's the relationship right here. Okay, let me just yeah, okay. So in the star configuration, the phase voltage, the line voltage is equal to phase voltage times square root 3. Now, somebody asked me to explain the square root 3, and I'm in the process of preparing that forever now. But in the meantime, I included a couple of YouTube videos that I have included in our playlist. So before I compose my lesson on that, you can watch those, and that's pretty much is going to help you, well, pretty good with that one, right? So so here's the line voltage we explained, and the phase voltage is, well, the voltage between any of the phases, any of the lines, and the neutral. So here is the E phase, pH, and over here, for example, would be the line voltage. Right? So here's the phase voltage across this coil, here's the phase voltage across this coil, here's the phase voltage across this coil, and here is the line voltage between these two lines. Here's the line, no, sorry, here's the line voltage between this one, this line, and that line. Alright, or between this line and this line, or between this line and that line, so that's the line voltage. Okay. Now, if it's a balanced system, things are pretty much, I use the term loosely, symmetrical, or equal. well balanced. If all the impedances are the same, all the voltage are the same, so then we have a happy situation with the setup that we have. All right, and these equations right here would be true. So, and also here, so the line voltage, so this voltage between those two lines, any two lines, and the phase voltage, you see the line voltage is going to be always greater than the phase voltage. Right? Now the line current is the same as the phase current. What does that mean? Well, here's the line current, and it's, well, coinciding with the phase current. Here's another line current, and it's also working together, same as another phase current. Here's another line current, and so on. Now, if the whole system is balanced, there should not be too much of the current happening on the neutral, although sometimes it will. All right, now when it comes to delta configuration, things are, well, the opposite. You see here in line in the Y configuration, or a star configuration of coils, the line voltage equals to square root 3 times phase voltage. Now in delta configuration, line voltage is the phase voltage, and the same relationship, right, same relationship that we have with the voltages in the Y configuration, we have the current. So in the delta, line current is square root 3. So you see here, in one configuration we have the voltages that are the same, and another configuration we have the currents that are the same, and the relationship between the voltages here in Y configuration is square root 3, and then in the delta configuration, the square root 3 serves us with figuring out the relationship between the currents instead of the voltages. Right? Now, how does that look? Over here, get my pen. All right, so this would be the Y, or sometimes Y configuration, or star. Three terms are being used. Right? Now for the delta configuration, we have basically a triangle. So here is a coil, here's a coil, and here's a coil. Right, and here's phase 1, phase 2, phase 3, right, or phase A, could be phase B, and phase C. Notice that the neutral, all right, is not connected anywhere. All right, so here is line voltage, E potential of the, well, sorry, this would be line, here's line, here's line, and the line voltage, of course, here, so this would be the E, the voltage, the line voltage, and if you notice, it's the same as the phase voltage. See that? Any voltage between any of those two lines is a line voltage. Right? Now the currents are going to flow the other way. The line current is not the same as the phase current, and here is the square root 3 relationship between those two quantities. Okay. Let me just make sure that I don't lose my windows here. Okay, so there you go. Now next slide here. Now here's a three-phase transformer. The question of why do we need three-phase transformers? Well, mostly it's the efficiency and the convenience of transmitting the power. Okay? So we have a generator which would generate, well, let's say high voltage, 1 kilovolt to 3 kilovolts. We could step the voltage up in order to transfer it over the longer distance. You see here we've got a step up transformer, and these are AC, right, voltages. We can step it up to 13 kilovolts, or maybe even 765, a few hundreds of kilovolts, and that lets us transmit the power over longer distance, because the power is, when you talk about RMS values, the power is the voltage times current. All right? So you could boost the current when you're sending the power over longer distances, or you can boost the voltage. When you boost the voltage, the current goes down, because the power needs to be transferred. The power is equal in both cases. So it's easier to boost the voltage to a high voltage and not have tremendous amount of current going through the lines, and that's how we can transfer power over the high power voltage lines, or the high voltage power lines. Excuse me. Efficiently, right? And then when we grab it from the high voltage lines, we use the step down transformer, and we get the power or the voltage to the homes, 120 or 240 volts, and factories you could get well, in homes usually you would get two phases. And there used to be some time ago that there would be a three-phase going towards the residential neighborhoods, and you would have two phases, and that would be you would get power from two phases, and you would have the square root 3 relationship between those two. Now there's something that's called, they're using center tap transformers, and they use the center tap from the transformers, the middle of the winding of the secondary winding, use it as a neutral. In that case, you have two sine waves on phase 1 and phase 2 of 240 volts, and then center tap, it gives you the 120 volts. Okay. And in that case, if it's a center tap transformer in the neighborhood that provides power to the homes, then you have the sine waves exactly 180 degrees out of phase from each other. So you could use 240 from your electrical panel, or you can use 120 volts depending what you need to provide the power for. Like, for example, if you want to connect the voltage to the outlets in the living room, so you can plug in your TV, and the TV power supply is designed to take 120 volts RMS, then you would just go from neutral to one of the phases. Okay, and electric range, the stove uses 240 volts, so then you would go between those two lines, and you get 240 volts. Factories, they get 600 volts, and it's a pretty much standard that they get three-phase power supplied towards the factories, as well as that, because factories also have offices that the computers plug in, and all the regular power supplies from everyday equipment. All right, so now all these power transformers are three-phase transformers. Those here, the step up and step down transformers, and you can have them wired. Well, what's a three-phase transformer? It's three single-phase transformers, right? You put them together and you get one three-phase transformer, right? So that's as close as I can explain this thing, all right? Now, connections, configurations, delta and Y. All right. Let's see here. Three-phase transformer, 3 primary windings and 3 secondary windings. Okay. How do I visualize this thing for you? so it's clear as you should have. Alright, let me just start another page here on my board. Alright, so you have a transformer, or you have a winding. Alright, now let's say we have another winding here of the secondary winding. Right? So that's a single phase transformer, whatever the ratio of the turns, how many wounds that thing has, you're going to have a ratio of something towards something. Let's say it's a step down transformer, and let's say, just for the sake of argument, the ratio is 2 to 1. So there's maybe 1,000 wounds and 500 wounds here. All right? And so the voltage ratio is going to be 2 to 1 on that single phase transformer. Now, what happens if we have, well, 2 more of those? Right? Here. Here. Oh, a bit of a jagged, but let's pretend that this is nice and straight. All right. Alright, so you have 3 transformers, and if you combine them in one kind of an area, common area, then you could have one 3-phase transformer. That you can plug in one phase to one, so phase number 2 to the other one, phase number 3 to the other one, and if the phases that are supplying the primary windings are separated by 120 degrees, then you're going to have the same thing on the other side. Now, how is it that what makes it a 3-phase transformer? Well, the connections. Right? You can connect the primary windings because physically they will look like this, and sometimes they're just one on top of each other. Right? Then that's fine too. That can be done as well. So those are 3 separate. You're going to have those leads coming out of the terminals, and how you're going to connect the primary and secondary, it's up to you. You can connect the primary in delta. You can connect the secondary in delta configuration. You can connect the primary in delta. You can connect the secondary in Y configuration, because if there are 3 transformers, 3 single-phase transformers, this first one here is going to be physically presenting its induction towards where is the first one here? Let's say this one here. All right? And the second one is going to project itself onto the second one, and so the physical configuration is not changing. It's how we connect those lines, how we connect the terminals, is going to make a difference. And in the lab tomorrow we're doing single-phase transformer. But how is it that we can do the connections? I'm going to start yet another page. All right, so let's see here. That's going to help you a little bit. Let's say we have 3 phases, and we want to connect a couple of those one transformer with primary and secondary. All right, so phase number 1. All right, we have phase number 2. We have phase number 3. Okay, so let's call them the phase A, B, and C, and let's have one more line here, and that is going to be the neutral. All right, so now let's say we're going to connect first one in delta, all right, on this thing here. So let's just there's a quick way of doing it, but I want to walk with you slowly so you can once you get the grasp when doing it slowly, you can just do a quick type of a configuration. You can just quickly look at things and see if the things are right or not. So that's what I use when marking your assignments. All right. So here we have a delta configuration. Let's say we number those transformers or those coils. All right. Coil number 1, coil number 2, coil number 3. All right. Now these are connected to phase. This is connected to a phase, and this is connected to a phase. Hello, Nico. Nice to see you. All right. So here is phase A. Here's phase B. And here's phase 3, C, the line. Now, neutral is not connected in the delta configuration. All right. Now, we're going to have on the other side, the secondary, we're going to connect things to, let's say, delta. Sorry, star. So we have a coil here. We have a coil here. And we have a coil here. All right, let's do that. Now, there is a line coming out of there. There is a line coming out of there. And there's a line coming out of there. And don't forget, in the star configuration, we do have neutral. So let's just assign them to phase A, phase B randomly, and phase C. See what comes up. And here is our neutral. All right. Now let's number those. Let's see. This is a coil 1, coil 2, and coil 3. So physically, coil 1 is acting on coil 1 here. Physically, coil 2 is acting on coil 2, and 3 is acting on 3 in a physical configuration. Right? They are just arranged physically that way. All right. Now let's number. See, we're doing it the slow way here. Let's number the terminals on each coil. So let's say coil number 1. This is going to be the terminal 1 of coil 1 and terminal 2 of coil 2. Okay. Then there's going to be coil 1, 2, and let's say 1 and 2. The terminals here on each coil, and here we're going to do the same thing. Let's say coil 1, terminal 1, 2. On second one, terminal 1 and terminal 2, and on the third one, terminal 1 and terminal 2. Okay. Well, in this case here, I'm going to bring those a little bit lower so we can oops, I need to yeah. Yeah. Bring them lower, and let's just reduce them in size a little bit so it's easier for us. Now this is here we have the configuration of delta and Y. Alright, so let's draw the transformers here, or on this physical configuration that we're going to do. Where's my layers? Sorry. There we go. Here's my layers. I'm going to choose the background here so I can write on things. All right. So here on the second, on the primary, we have the first coil. We have the second coil. We have the third coil. And on the secondary side, we also have coil, we have coil, and we have a coil. All right. Now, how are we going to connect those into those lines? So let's say this is 1, this is 2, this is 3 for primary, this is 1, this is 2, this is 3 for primary. We're just corresponding those to these here. And terminal 1, 2, 1, 2, 1, and 2 on those, and the secondary, terminal 1 of the first one, terminal 2 of the first one, now terminal 1 of the second one, terminal 2 of the second one, and so on with the third one. All right. So how are we going to connect these physical coils to the phases, so we can have the connection like that? So the first thing I'm going to do is I'm just going to break those phases, break those lines. Alright, see that? Actually, let's do this here. There we go. That is going to work right now. All right. So, all right. So here is A. Oops. Here's A. Here's B of the secondary, here's C, and here's neutral of the secondary. So here's the primary, and here's the secondary connection here. All right. Now, this is going to be simple right now. The coil number 1, all right, terminal 1 goes to B. See that here? So terminal 1 goes to B. Connect. Right. Terminal 2, right here, goes to A. It's connected. Now, number 2, terminal 1 goes to A. Terminal 1 goes to A. Terminal 2 goes to C. See that here? Terminal 2 goes to C. And number 3 here, terminal 1 goes to C. And terminal 2 goes to B. This is how we connected those. According to this, we just transferred that from here to here. But there's a quicker way you can do that once you get this idea here. So each of those coils are connected to 2 separate lines. And we have a delta connection here. Number 1 goes to A and B. All right. Number 2 goes to A and C. And number 3 goes to C and B. All right. Now, same thing with the star configuration or Y configuration. Coil 1 goes to A. Terminal 1 goes to A. Coil 1, terminal 2 goes to neutral. Notice that in delta, neutral is not connected. Now, number 2 coil, terminal 1 goes to B. In this case here. All right. And terminal 2 of the second coil goes to neutral. And 3, of course, we have used A, B, now C. Right? Terminal 1 goes to C. And of course, terminal 2 of the 3 is connected to the neutral. So this is connected here. This is connected here. Physically, they are arranged, so one acts on the other. So 1 acts on 1 here, 2 acts on 2, 3 acts on 3. And if you have 3-phase power supply going into the primary supply connection here, due to induction, how the transformer works, we're going to have the voltages appearing on the secondary three-phase. So this is how you can, well, isolate the whole thing one from another, the coil, primary coils and the secondary coils, and you can connect delta to delta. You can connect delta to Y. You can connect Y to Y. The choice is yours, depending on how you would want to for the thing to work. Right now, notice that in the secondary, when it's star, we have neutral, so we can grab the phase voltages and line voltages, and currents are going to have the relationship different than the currents here, and the voltages are going to have different relationships than the voltages here. Okay, so that's you're going to need this type of knowledge that I just gave you when you get to the three-phase transformer, and that's going to be your next lab after this week, because this week you have with me, and Mr. Hager is going to continue with the second half of the semester after that. All right. Hey, Evan. People are coming and going. You must be having some really heavy something that you're getting ready for, that everybody is so busy. All right. Cool. All right, everything is being recorded, so you can watch it on your own time. All right? I'm not going to give you a hard time. All right, so we have the three-phase transformers, primary, and so three primary windings, three secondary windings. Physically, they act onto each other, and if they are not connected, they are just acting upon each other. If you have the supply on one, it's going to act on only one on the secondary, and if you only have on the other primary, it's going to only act on the other primary. Right? And how is it that we do these type of connections here? Determines on what kind of system we're going to deal with and what kind of calculations we're going to be up against. Okay. So in this case here we have delta to delta configuration, and over here we have delta to Y, which we just did the connections type here. All right. All right. So what else can we see here? Here's the primary H1, H2, 1, 2, 1, 2. Okay, primary. They are. I don't think they are labeled here. Which one is one? Oh, they are with colors. Okay, so here's red. All right, that acts on this. This here in yellow acts on that one, and that one acts. This is how they are arranged physically. All right, and over here is that. Physically are the same arrangement. It's just the wiring of the terminals that determines what system. Oops. Yeah. This relationship right here. When we do the calculations, we have to apply the numbers to whichever configuration or topology we have applied. All right. Now, three-phase transformer, three primary windings, three secondary windings, connections, Y to delta, there's Y to delta, and Y to Y. This is how we would do. And you see, if you number them, you can transfer that to actual connections. Okay. Now the voltages. All right. We have how to find the voltages in the three-phase transformer. Primary, secondary, line, and phase follow the power flow. Well, the power is the power. What do transformers transform? Transformers transform voltage, they transform current, they transform impedance, but they transfer power. They keep the power. All right, so let's see here. Here we have the power supply, so here's the generator, and here's the load. So we're going to, when you see the E with that notation of G, that's the generator. Okay? And that's also referring to the primary side of the transformer. 4 steps: source, primary, secondary, load. All right. So source, assume Y connection for three-phase generator. So here we have the coils, here we have the neutral A, B, and C. These are the phases that is going to produce. This is the supply, the generator, and the phase voltage. The phase voltage. The phase voltage is the voltage of phase A to neutral. That's the phase voltage. Or phase B to neutral. Phase B to neutral. And phase C to neutral. Phase 1, phase 2, phase 3. And of course, if this is a balanced system, things which means those impedances of the coils and everything is the same, just repeated 3 times as far as the equipment that's being used, and it's connected in a balanced way, then those are going to be equal, right? This voltage here is going to be equal to this voltage here, and it's going to be equal to this voltage right here. Now, line voltage, again, what is the line voltage? It's between 2 lines. It's between the 2 phases. So, the line voltage, as opposed to the phase voltage, would be this voltage here, between B and C, or between A and B, or between A and C. And again, if the system is balanced, which means all components are equal, and they're connected in such way here, then those voltages also going to be equal to each other with a phase shift, right? But the values, the magnitudes are going to be the same. And here is the relationship again. The line voltage is square root 3 of the phase voltage. Sorry, square root 3 times the phase voltage. See here? Yeah. That voltage is always going to be greater than this voltage here. Here's the relationship, and we keep going. Primary winding according to delta and y, secondary winding voltage according to turns ratio, all right, and okay, so primary winding voltage according to delta and y. So you look at the primary side and see if it's a delta or y, then you're going to use the relationships, the square root 3 between the voltages or square root 3 between the currents. In this case, the delta line voltage is a phase voltage. Because see, here's a phase, here's another phase, here's another phase. The phase voltage is the voltage across the phase. And in this case, it's the same as between the 2 lines. So in that case, in this case, phase voltage is equal to the line voltage. And the relationship between the currents is going to employ that square root 3. Right? So line current will equal to is equal to phase current times square root 3. In the star, it's the opposite. The currents are the same, and the voltages are depending on the square root 3 relation. Secondary winding voltage according to the turns. All right, well, physically they're arranged. So this primary coil, see the red coil, indicated with a red square. So let's say coil number 1 is acting upon the red coil. Here, physically they're arranged, they're built that way in the transformer. So depending on the turns ratio, let's say this one has 1000 turns and this one has 500 turns, so the ratio is 2 to 1. And if you put 100 volts here, use the ratio 2 to 1, you're going to get 50 volts here because you have less turns. And of course, the current is going to be higher here because the power has to be kept. And the current is going to be lower here comparing to this coil here because the power has to be kept. Power equals voltage times current. You raise the current, you're going to diminish the voltage. You raise the voltage, the current is going to be less because the power primary and the power secondary, there has to be the equal sign. We'll have to keep that equal sign there. Right? All right, so, and the line voltages according to delta and y, depending on how, okay, we have to look. delta or Y. This is delta, so I'm going to use the delta relationships between currents and voltages in this section here, and then we'll take a separate look on that. So when we know the turns ratio, we'll be able to tell what voltages are, what voltage is on here, and what voltage is on here, and what voltage is on here, and depending on whether it's delta or Y, delta in this case, then we're going to be able to tell what the line voltage or the currents relationship is. Here's an example. I got two examples for you here, and I'll let you go. All right, so like everybody, Evan and Evan. Okay. All right, so okay, here's a example. 3 transformers with turns ratio of 2 to 1. So we know that the relationship between here and here is 2 to 1. Twice as many wounds here than here. So this voltage will be half of what this voltage is. Okay. Are connected in delta to delta. So that's important information, that we have delta on one side and delta on the secondary side. And we have 3-phase 208 voltage source. So 208 voltage source, this is the line voltage. Sorry, phase voltage, 3-phase 208. Yeah, that's the line voltage source. 3-phase 208 voltage source. That is the line voltage. Find the voltages in the system. All the voltages in the system. Well, okay. So what do we have here? The generator, the voltage of the generator side, generator here, line equals 208. Write it down. All right. Now, the relationship between the phase voltage and the line voltage is that they're equal, because here's the phase voltage across the coil, and here's the line voltage between the two lines, and you could see that they are connected here and here. They are the same. This voltage equals to this voltage. All right, so phase voltage is equal to a line voltage, looking at the primary here only, and it's going to be 208. So the phase voltage is 208 and the line voltage is 208 in this case of delta. All right, now on the secondary, first we got to find out what this voltage is. We know what this one is. We know the ratio, so we have 208. So the ratio is 2 to 1. So twice as many wounds here than here. So this voltage is going to be half of what is here. So we're going to have 208 divided by 2. We're going to have 104 volts. So we know that the phase voltage is 104. And, well, what's going to be the line voltage? Well, it's a delta, so line voltage equals to phase voltage, also going to be 104. Right? And load, well, voltage of the secondary load across the load. All right, we're going to have 104 line voltage. All right. So what is the voltage across the load? They're asking for the line voltage. It's kind of unspoken, but we just spoke that. Okay. All right. So now we have delta to delta. One more example. All right. I did this one for you here. Now we have delta to Y configuration here. This coil acts on this coil in green acts on this coil in green. That's how they are physically arranged. All right, we got the same thing. 3 single-phase transformers with same ratio 2 to 1 are connected in delta Y configuration to a 3-phase 208 source. See here, it says 3-phase 208 source, which means the line voltage is 208. volts. Line voltage. Line voltage is between two phases. Any voltage between any two lines. So AC, we're going to have 208. Between C and B, we're going to have 208. And between A and B, we're also going to have 208. Same magnitudes, again, arranged in a way that they're separated time-wise, 120 degrees from each other. All right, so let's see. Same thing, find all the voltages in the system by calculating first. What's the source line voltage, primary phase voltage. So what's the line voltage on primary? What's the phase voltage on primary? What's the secondary voltage on the phase voltage? What's the secondary line voltage? And load line to line voltage. And you'll see I'll put a bit of a smile there. Okay. All right, so here's the answers. Okay. I'll give you the answers first. And the next page is the details, are the details on how we got to it. Right? Now, but I'm just going to explain it quickly. Source voltage, line. Well, we're told that it's a 208 source, which means it's the line. It's the line voltage, 208. So between those two lines, we have 208. Between those two lines, we have 208, and between these two lines, we have 208. So 208, 208, 208. Because, as we noticed before, phase voltage is equal to line voltage in delta configuration. Different case in the Y, but we're not looking at the Y yet. We're just looking at this side here first, because they're asking us for source line voltage and primary phase voltage. Primary phase voltage, they're equal to each other, so it's also 208. We don't even need a calculator for that one. Secondary phase voltage. Well, how do we get the phase voltage? If we know the phase voltage on primary, and if this coil is acting on this coil, and we know the turns ratio, which is 2 to 1, so this phase voltage, that's all we're concentrating on right now, is going to be according to the turns ratio, which is 2 to 1. Then if this one is 208, well, this one is going to be 104. So here's 104 across this coil, 104 across this coil, 104 across this coil. All right, so we have that secondary phase voltage, 104. Now, how do we get that 180.13 volts? Let's see, here's the hint, here's the formulas. Here are the formulas. In delta, phase voltage is equal to the line voltage, and the phase current, line current is equal to phase current times square root 3. So if you want to calculate the currents, we would use this formula here, if we knew the power. But here's just the relationships. Now, what is the line voltage? Because we know the phase voltage in the star configuration, but in star configuration, the line voltage is not equal to the phase voltage. Well, it can't, right? Because this is here, and this is here, and between those two is some sort of a combination of this voltage and that voltage. Is it twice? If this is 100 volts and this is 100 volts, are we going to have 200 volts? No, because we have the 120 degrees shift, so we need to use that square root 3. So we know what this voltage is because it's half of that. So now we have this one here, it's 104. If we want to know what this voltage is here, we just multiply that by square root 3, and we get 180 volts. What's the line to line voltage? Well, it is the line voltage, right? So here, I wonder if this was some sort of like a tricky question just to make sure that we understand the line voltage and line to line voltage that are basically the same. That's what it is, because line voltage is the line to line voltage. Right? So here is the details on how we did that, how we explained that. You understood that now. I hope that you did. when I was explaining, but you can just look at that. So I'll just put the smiley face here because the line voltage is the line-to-line voltage. And this is the details on how I got. This is basically everything that I just explained on the previous page. Okay. In summary, three-phase transformer. We have a primary and a secondary, and we have the line and phase quantities. So primary and secondary. How is it that those things are physically arranged? Well, physically this one is arranged. So you could have three coils beside each other on the primary, and three coils beside each other. So this one is arranged. So this one is acting on this one is acting on that one, and that one is acting on this one. Or sometimes they're one on top of each other on the same core. Right? So primary, secondary, and we have the coils acting upon each other, and we have delta or Y configuration happening here. All right, and the relationship between the voltages and the currents, it's on this here on this slide. In the Y connection, line voltage is equal to square root 3 times phase voltage, and the currents are the same. Line equals phase current, and it's just the opposite on delta configuration. And the apparent power is square root 3 of times line voltage times line current. All right? The apparent power, VA. And it's also, the relationship is given to you in the first example, or the second example right here. Here are the relationships. Okay. So as I said, again, there is going to be a test. Next time we see each other, it will be a test. So look at the quizzes that I posted. They are short quizzes, short 5 questions each. We did that yesterday. So whoever was present yesterday in our in-person class, you're going to have, it's going to be a breeze for you to go through those quizzes, 2, 3, 4, and 5. But it's an open line quiz, so if you are stuck on something, you have the options for calling a friend or doing a shout out on the street or whatever. So make sure you're comfortable with those. Those questions will, solving and understanding how to approach that, what we did yesterday, is going to help you write the test. And whoever was not present, then it's, well, that's true. I strongly recommend that you do that, those quizzes, and I put them back to back. Back has put the quizzes back to back. So when you go through that, you're going to have fresh mind when it comes to those ideas. It's not like you did the quiz 3 weeks ago and now in person test in class. Then you're being asked that question, and you're being asked to solve that, something that you did 2-3 weeks ago, and in the meantime you were dealing with other subjects and all that stuff. So if you do those quizzes, please do that before Tuesday, because on Tuesday there will be a test. Test will be on Tuesday 15th, June 15th, during our regular in-person class time. Right? That's it for today. Thank you for showing up, Evan. And whoever didn't show up, maybe you are busy with some other subjects heavily, then you have the option to view this thing on YouTube. Evan, you might want to send email to everybody just so they know. The test is being announced in the course plan since the beginning, so that's normal. But then again, it was mentioned a couple of times. Yesterday during in-person class, and now during the online class was also mentioned. And just maybe a bit of reinforcement of the written stuff which is in the course plan. I'm going to send email just to remind everybody. All right, thank you so much, and I will see you when I see you next time.